It is a great pleasure, a real pleasure to have with us Snezana Stanimirovic, who is a professor at the University of Wisconsin at Madison. Snezana obtained her PhD from Australia. She comes originally from not very far away from, from Crete. Crete is, as we say, the largest island of Africa after Madagascar, but she's very close to Greece. She comes from Serbia, where she did her undergraduate studies in Belgrade, and then got her PhD in Australia. And then we overlapped because she was for several years a postdoc at Cornell and Arecibo. And then she moved to the Golden State, where she spent a few years at Berkeley before accepting a faculty position at Madison, where she has been a professor for the past 5 years. Snezana has been working on various topics related with the ISM properties of galaxies, both atomic and molecular. And we will have the pleasure today to hear about her latest results and the colloquium, which is entitled New Perspectives on the Neutral Interstellar Medium from the Milky Way to Nearby Galaxies. And without further ado, Snezana, thank you.
Thanks so much, Vasilis. It's great. It's great to see you, and it's great to be here. It's a virtual get together. Good morning, good afternoon, good evening, wherever you are. And I just remembered, yes, Vasilis, like I think you and I met probably around year 2000 or so. So it's been quite a long time. I'm very glad to be here, and I want to focus today on some properties of the neutral interstellar medium, and I will be sort of switching between the Milky Way and several nearby galaxies, and there is a really big reason for that. Essentially, right now we are at a very special time when we have high resolution and sensitive observations for nearby galaxies. And essentially a lot of the science that we for a very long time were able to do only in the Milky Way and address some questions only in the Milky Way, now we are at a very important threshold when we can move on to nearby galaxies and do similar work and really explore a very interesting new parameter space with different metallicity, different interstellar radiation field. And so I will be focusing on some recent results, but I also want to show you some very new, very preliminary results that my group has been working on, and hopefully get some feedback. Halfway through my talk, I plan to pause and have some time for questions and sort of try to have a little bit of a more interactive conversation. So let's get going. So the neutral interstellar gas has this very special place in terms of the interstellar medium. It's sort of sandwiched in between hot and warm ionized medium and sort of denser and colder structures then leading to star formation. So typically in galaxies, when we look at the global mass in terms of across different ISM phases, neutral gas usually plays the dominant role. So from that point of view, it is really important for the process of star formation. Also, we know that molecules form on the surfaces of dust grains from predominantly neutral atomic gas. So that's another very important role that the neutral gas plays. And as you will see throughout this talk, there's a lot of very important shielding that neutral gas provides for the formation of molecules. And further on, somehow atomic clouds collide or something else happens. We still don't understand how these processes go fully, but atomic clouds turn into molecular, dense and cold clouds, which further lead to star and planet formation. So there is this very important link. And throughout their life, stars inject energy, momentum, different chemical species back into that interstellar medium, providing stellar feedback, which, as you will see in a moment, strongly shapes that neutral interstellar gas. So there is this complex feedback loop. So we now have very high resolution observations and can study the neutral atomic gas in the Milky Way and nearby galaxies at high resolution. This image comes from the GALPHA collaboration. So this is a Arecibo survey of the Milky Way with an angular resolution of 4 arc-minutes, which really means when we look at nearby molecular clouds, that really gets us down to sub-parsec scale. So this is really great. We can start now in the Milky Way to resolve and study that neutral gas that's right around molecular clouds and study essentially formation of giant molecular clouds and the role that the neutral gas plays there. So this image shows, it's a combination of 3 different velocity channels shown in slightly different color, just to kind of give you an idea of the depth and complexity of the structure we are seeing. And as I've been trying to emphasize, basically, we are at the point where we can look at nearby galaxies at essentially very similar angular resolution. This is the small Magellanic cloud as viewed in H1. This is the 21 centimeter line of atomic hydrogen. Again, color just shows 3 different velocity channels, just to show a little bit more complexity of the structure. These are observations obtained with the new interferometer in Australia, ASCAP, or Australian Square Kilometre Array Pathfinder. And this image was obtained only as a sort of part of a commissioning effort. So essentially, we used 1/3 of the interferometer that was available and obtained spatial resolution that's basically down to 10 parsecs. So right now we can do a much better work and get down to really even smaller spatial scales. But you can see and appreciate the complexity of structure. There's lots of different filaments, holes. It's a really bubbly and complex neutral gas. So numerical simulations are telling us that in order to explain a lot of things we see in that neutral gas and also even further dense molecular gas in galaxies like the Milky Way, like the SMC, we need to implement stellar feedback. So this is just an example. This is work by Phil Hopkins that demonstrates that essentially to reproduce a morphology of neutral gas that we see in observations, we need stellar feedback. The situation is such that numerical simulations are now starting to argue which kind of feedback is more important and what role different feedback channels are playing. And there's a lot of uncertainty at present. What's really more important, whether it's thermal influence of H2 regions, whether it's supernovae. However, it's well known that unless numerical simulations include stellar feedback, the density they produce in simulated galaxies, as shown at the bottom right-hand panel as a dotted line. So the density reaches artificially high values. Essentially, galaxies are produced with way too much dense gas that then leads to runaway star formation and produces star formation rates in galaxies that are extremely unrealistic. So essentially, feedback needs to be included not only to reproduce the morphology of galaxies, but also to reproduce the gas fraction as a function of density. And on this graph, they basically show different feedback prescriptions in different colors, and they're sort of just trying to tease out and say which feedback channels are more important. Also, some numerical simulations go even further to look at some properties of giant molecular clouds. So on the bottom left-hand side, you see an example of so-called Larson's law, where on the x-axis we have a log of the size of GMCs and the standard deviation velocity dispersion on the y-axis. And in order to reproduce realistic Larson's law scalings, we need also a lot of stellar feedback. So yeah, so stellar feedback is really important. And sort of let me just get back to that global picture of where things are in terms of interstellar phases. So there's still quite a few things that we don't know about our own Milky Way and the neutral gas in our own Milky Way. And as you will see in a moment, once we start moving into nearby galaxies where metallicity and interstellar radiation field are very different from what we find in the Milky Way, we are totally in a new territory. And a lot of our standard theories have not been tested fully. So in this talk, I want to focus on three different parts. So the first one is looking into thermal structure or thermodynamics of the neutral gas and essentially trying to constrain the excitation temperature of neutral gas, and also look at how high above the Milky Way plane cold gas can get. And then I want to start looking a little bit into shielding of molecules that's provided by the neutral gas. And at the end, get back to stellar feedback, which is something where ASCIP is really paving the way and allowing us to do some interesting new work that we were not able to do previously. So I have some cartoons here. Some of the projects I work with, we call 21-SPONGE, and then we have ALMA-SPONGE. So you'll hear about this in a moment, and I'll explain what does that mean. Okay. So thermal structure of neutral gas. So basically the theory tells us that heating and cooling processes in the interstellar gas or in the interstellar medium tell us basically conditions at which we expect to see multi-phase gas or gas at a range of different temperatures. So most often we like to plot that as a phase diagram, which shows thermal pressure as a function of density. And the black line here is sort of a theoretical curve, and the dots in color, red and yellow, come from Patrick Hannibal's numerical simulations. So essentially, this pressure curve has this very characteristic saddle or sine-like wave pattern. And this is telling us that in order to have a range of temperatures in neutral gas, for that to happen, we need to have only very specific range of thermal pressures. So yes, at the solar metallicity and the conditions typical for the solar neighborhood, only at a very narrow range of thermal pressures, we expect to see colder neutral gas with a temperature of, say, 100 Kelvin, and warmer neutral gas with a temperature of, say, 8,000 Kelvin. And unless there's a lot of turbulence present, the land in between, which is thermally unstable neutral gas, should not be very well populated. A more kind of a recent view into all of this, it was provided by Shmuel Bialy, 2019 paper, where he really tries to highlight the importance of underlying properties like the gas metallicity that goes into providing photoelectric effect and also cooling. How important role metallicity and also interstellar radiation field play for the existence of that multi-phase medium. So you see, like in this diagram, you can have cold gas in blue versus warm gas in red, and for both to exist, that requires a very narrow range of pressures, and that gray sort of triangle changes depending on metallicity of the medium and also cosmic ray abundance and also interstellar radiation field. So the basic point is, once we move to nearby galaxies, which have different metallicity, different interstellar radiation field, we expect to be able to probe these new regimes different from the Milky Way and see how that multi-phase regime changes. So let's look at the Milky Way, because essentially understanding of thermal structure of H1 was until very recently possible only in the Milky Way. And even in the Milky Way, things were sort of complex. So if you look at the right-hand diagram, this is essentially a snapshot of that phase diagram. If we were just to plot the PDF of gas, of neutral gas or H1 as a function of temperature, we would expect to see bump that corresponds to the cold neutral medium and another bump that corresponds to the warm neutral medium, and then land in between is thermally unstable. So for a long time, we have been able to look at the H1 in absorption against background sources, and using absorption lines, measure the temperature of gas. But as you can see on the left-hand side, for most of the time, we were able to just probe that cold neutral medium. So we've been able to do that for a long time and to do basically constrain the temperature of the cold neutral medium very well. But the obvious thing is what happens further with that PDF. Basically, can we constrain the warm neutral medium? So where is it essentially? There have been only some limited observations at super high sensitivity, like example shown at the bottom by Varkanant et al., where occasionally when looking at very strong absorption lines, we were able to see a tiny little very weak shoulder that would correspond to a warmer temperature, and that can be, that was suggesting that a warm neutral medium exists with a temperature of about 4,000 Kelvin. But those observations were extremely rare because the warm neutral gas has high temperature and low optical depth, so we need super sensitive observations to get down to those low optical depths to be able to see it. Okay, so a few years ago, my collaborators and I decided to use the very large array and to sort of do a systematic survey in the direction of 57 radio background sources at super high sensitivity to try to go after that warm neutral medium and statistically measure its temperature and really probe that diagram and see essentially is that warm neutral medium bump in the right place or not. And another important thing is, of course, constraining that thermally unstable gas. There have been many numerical simulations predicting the fraction of that thermally unstable gas, and the predictions were sort of all over the place. So this work, we focused on 57 background sources and obtained very high sensitivity H1 absorption spectra using the VLA. This is the distribution of our sources. We mainly focused at high galactic latitudes because the spectra are easier to decompose there, and there's not that much confusion as opposed to going right through the galactic plane. So this beautiful work was part of Claire Murray's PhD thesis, and Claire is now an NSF postdoctoral fellow at Johns Hopkins University. For this project, we also teamed up with Kim and Ostreicher to use their numerical simulations, which predicted and gave us essentially 10,000 of synthetic hydrogen spectra. And the idea was, by knowing the answers, the concrete answers, we can then run our analysis techniques and really figure out any potential biases that were affecting our measurements of the spin temperature or the excitation temperature. So this was really possible only because of the upgrade of the very large array. So I have this little movie that shows 3 different measurements obtained in the direction of the same background source. So this is a VLA before the latest upgrade, where you see some absorption lines, but this is sitting on top of like a lot of wobbly structure that's really not real. And then halfway through the upgrade, we got a different spectrum. Basically, a lot of this wiggly structure has disappeared. And then at the end of the upgrade, we were able to really clean this very well and pull out very high sensitivity observations. So yeah, so this project was really possible with the latest VLA upgrade only. So as I said, we worked with synthetic data, trying to constrain, first of all, our completeness of our survey. And as you can imagine, we are trying to isolate different absorption lines, and then the question is that does that really correspond to physical structures or clouds in the, say, simulated data? And that allows us to sort of quantify the completeness in a way that once we work at low galactic latitudes, we're actually having a lot of confusion and we are missing a lot of real structures just because spectral lines tend to get very close together. But at high latitudes, we are doing an excellent job and have a completeness of almost 100%. And another useful thing is with numerical simulations, we know the answer to what the temperature should be. So we have used this to to test our radiative transfer calculations we use for calculating and estimating the excitation temperature, and basically figure out which temperature regimes are easier for us to constrain and which are worse. So let me show you the result of that work, which actually took about 600 hours of VLA observing time. So it took quite a few years. So here is on the right-hand side that theoretical diagram, CNM, WNM, thermally unstable gas, and here is on the left-hand side in gray what we obtained. So from there, we were able to constrain in terms of mass that about 30% of H1 is the cold neutral medium, and of order of 20% is thermally unstable, and the rest, things we could not really see in absorption, corresponds to the warm neutral medium. So some of you are probably aware that the fraction of thermally unstable gas has been is something very interesting, and many numerical simulations have pointed out that the more turbulent the neutral medium is, the larger fraction of gas will be in that unstable regime. And the sort of the predictions have been going all over the place, anywhere from, I would say, 10% to 50%. So our estimates are pretty kind of in the intermediate range, and it's very reassuring to see that the more recent numerical simulations, which have been even playing with different values for the heating curve, and have constrained and suggested that thermally unstable fraction is of order of 20% or even lower. So basically the numbers of the fraction of the thermally unstable gas over the years have been sort of dripping down slowly, and it's nice to see that observations and simulations are agreeing right now. One interesting thing to notice is when you compare these two graphs is that we are not detecting very much of the warm neutral medium in absorption. The survey was defined and we really tried to reach sensitivity good enough to detect any warm gas with a temperature less than 4,000 Kelvin, yet we had very few detections. What's going on? So, we ended up taking our absorption spectrum, removing any of sharp absorption lines we could find, and then shifting to the central velocity, and then stacking the results back both in absorption and in emission. And only then we were able to see this very broad and very weak absorption feature with a peak optical depth of only like 10 to the minus 4 and the width of 50 kilometers per second. So this is interesting. So this is a statistical detection of the warm neutral medium in absorption that suggests temperature of 7,000 Kelvin. And this is a little bit puzzling because of the following. So the connection between the excitation or the spin temperature and the kinetic temperature is not always one-to-one. It's a little bit complex. So at low temperatures where gas density is higher, collisions are frequent enough and are able to thermalize the 21 centimeter transition of atomic hydrogen. So basically, at low temperatures, we expect the excitation temperature of H1 to be the same as the kinetic temperature. However, as the density gets lower, meaning that gas gets warmer, the spin temperature starts lagging behind the kinetic temperature just because the collisions are not frequent enough and the line is not thermalized anymore. There is an additional excitation mechanism for the 21 centimeter line, which is via Lyman alpha absorption. So essentially, if we have a good pool of Lyman alpha photons, hydrogen absorbs the Lyman alpha photon, gets excited, then gets de-excited, and a certain percentage of time during that de-excitation process, the 21 centimeter line will stay excited for that spin flip transition. So however, the current theoretical models and numerical models, even after including that secondary excitation mechanism, suggest that flattening of the spin temperature and the plateauing at about 4,000 Kelvin. So the bottom line is this means that when we do our measurements, we should not see warm gas anywhere with a temperature higher than 4,000 Kelvin. What we detect is 7,000 Kelvin. And there were several additional measurements with the temperature higher, like of order of 4 to 5, 6,000 Kelvin. So there's something interesting going on here, something that we still don't fully understand. So one idea is that the Lyman alpha pool of photons is larger and that needs to be incorporated properly. So essentially that secondary excitation mechanism could be more important than what we have considered so far. Or the other thing is that there could be something interesting going on with the radiative transfer and that's still not fully incorporated. But basically the results from our 21 sponge survey are that yes, we detect CNM, we detect the WNM, but that peak of the WNM has to be shifted a little bit to the right. And I feel there is still quite a bit of work to be done to understand whether it's a really radiative transfer or it's the Lyman alpha flux that we don't understand fully in the Milky Way. So I will now move on to several other, couple of other more recent projects that have sort of started as a follow-up of the 21 Sponge project. So by the way, I should say the name for the survey 21 Sponge came from the fact that most of our observations were obtained during the scheduling gaps for the VLA, essentially the time that nobody else could use. So we sort of saw ourselves as just sponging away any unused telescope time, any tiny little gap, just give us that time and we'll use it because we needed to accumulate really a lot of integration time to get our sensitive spectra. So one other question that my graduate student, Dan Rybarczyk, who may be listening and is present during this talk, is what is the CNM scale height in the Milky Way? So basically now we have this beautiful spectra for 21 Sponge, and there have been several additional absorption line surveys, and sort of then combined all of that information. And for lots of directions, when we decompose spectra into a bunch of absorption lines, we see several lines. So essentially then combined a database of about 800 different components. And so we are showing that here the galactic longitude and velocity diagram. So you see the blue dots that show our sources, and we don't have uniform coverage. Of course, we are really lacking in the information for the fourth quadrant, which is something we can see only from the southern hemisphere. So we know that the radial velocity of the CNM clouds, or the CNM features or structures, it's really determined by the galactic rotation. And if we focus on the region very close to the sun, the expression for the radial velocity can get expanded in a Taylor series and can be expressed in terms of Orth's constant A, a bunch of sine L cosine B factors, turbulent velocity component, and the scale height for the CNM. So essentially that Z is telling us how high the cold gas gets above the plane. And sort of this is an interesting game. So essentially by using this expression for the radial velocity and having lots of radial velocities for a bunch of clouds, we can figure out that Z. And several previous studies have played that game and constrained the scale height for the CNM of order of 100 parsecs. So we wanted to do the same, especially now when having such a large database. And so here is Dan's result. So essentially by changing the maximum radial velocity for the clouds we include in our calculation, we can calculate the scale height. And you can see that when we are very close to the sun, the velocities are very small and the scale height keeps increasing. And then once we essentially include all of the CNM clouds in the solar neighborhood, the scale height flattens at about 120 parsecs. So this is nice. So this is really great, and we are essentially confirming previous results. But one interesting thing is, by having so many data points, we want to really address the question of, does that scale height vary locally around the sun or not? And this is something that has not been done previously. through H1 emission data, we have a pretty good information about the global low resolution structure of the Milky Way disk. And this is beautiful work by Evan Levine, which shows that in the outskirts of the Milky Way, there is a dominant warping of the disk, both warping and flaring. And then on top of that, all this very small scale ripply or oscillating structure that's present in the warp. And some work has been done previously trying to show that the origin of that, and the idea is that as the Milky Way gravitationally interacts with nearby galaxies, a lot of those gravitational forces are introducing special like ripples in the disk structure. So yeah, so now we've done something. This is a very preliminary result. So essentially, if we try to repeat our scale height calculation for the range of galactic longitudes shown in blue, where we expect the most dominant warp effects in the outer galaxy, we can get one curve for the scale height. But if we take all other longitudes and repeat that calculation, we get the red curve. And essentially what we are seeing is that in the region where the warp is present, we find a higher scale height than everywhere else. But just to remind you where we are looking with our sample, it's really mainly within that orange circle. So essentially we're looking very close to the sun, and we are starting, I think these measurements are really telling us that we're starting to see some small scale fluctuations in the cold gas distribution, which are suggestive of evidence that the warp is present all the way to basically solar neighborhood. So while previously we were able to just focus on the outer portions of the Milky Way, now we can get in close into the solar neighborhood and see how is that privileged structure looking like. Okay, so we can talk more about this if you have some questions, but I think I need to move on. So this 21 sponge survey was really great because it really gave us in the direction of 57 background sources, incredible diagnostics of what's happening with neutral gas. So we have the kinetic temperature information, we have the turbulent information, we have the column density information, and of course we decided to follow up with ALMA. And so we picked about 20 millimeter bright ALMA sources and obtained observations. So we looked at several molecular species, HCO+, HCN, HNC, CCH. And this is just an example of two of our sources where essentially both sources have beautiful and strong H1 absorption, yet in terms of molecular abundance, they're extremely different. 3C111 has very strong molecular lines, even to the point of saturation, while 3C138 has essentially no molecules. So what's really driving, what sort of environmental conditions are driving this molecular diversity, and what can that, basically what we want to understand is, can we use H1 diagnostics to figure out what physical processes and conditions are more suitable for molecule formation? So one of the first things we did was to look at the column density of all these different molecular species as a function of total gas column density, which is something we have very well now from H1. And you can see that at column densities of 10 to the 20, there are no molecules. Once we reach few times 10 to the 21, suddenly molecular abundance increases. And what this is really telling us is that what molecules care about is the shielding that's provided by neutral gas. So basically neutral gas along the line of sight is mixed with dust, and dust absorbs radiation, surrounding radiation, warms up, re-emits in infrared, but by doing that, it essentially protects and saves molecules from dissociation. So that's really, that shielding plays a crucial role in building up molecular abundances. So this is nice, and I don't think this was done previously for this particular species. We have known for a long time that the same thing works for molecular hydrogen, This is an example from the Perseus molecular cloud, observations in black against the theoretical models on the right-hand side, where similarly we need, essentially there is no H2 until you reach a column density of 10 to the 21, and at that point molecular abundance starts shooting up. Yeah, I just need to check my time. Yeah, so I think we're good. Yeah, so we are working with Munangong and Eva Stryker and others, trying to compare our observations with their numerical models, which included more complex chemical reactions, and trying to figure out if we can tease out whether turbulence or some other local interstellar conditions are more important for molecular abundances. But I'm going to stop this part of the talk here and pause for a second to see if you have any questions before I move on the last part of my talk. So yeah, so there will be a lot more to come from ALMA-SPONGE. We're also having some additional observations with NOEMA, and we're building up our sample. Any questions so far?
Well, actually, I have a talk, but I have a question, but maybe when you are calculating this, you know, the abundance variation and the models as a function of, say, galactocentric radius, what you measure is velocities, right? Do you need to make an underlying assumption about sort of like a model of our galaxy in order to actually place them in a specific distance? And how,
yeah,
because I was thinking, you know, similar, well, you know that, right? I mean, for high velocity clouds and things like that, there is a certain uncertainty on the distances, right? And if we talk about flaring up a bit of the disk, I was wondering whether this introduces an uncertainty which is not very well controlled.
Yeah, yeah. So you're absolutely right, Vasilis. So yeah, so I have simplified this. There is one additional term here that we are working with. And so yeah, so basically this whole model assumes circular orbits for clouds around the galactic center. So no radial motions, just very simple circular orbits. And there are, and so there is another potential parameter space that we need to explore, which is really related to some decoupling between stellar and motions of H1 clouds. So yeah, so we are working on that too. I just didn't want to get into more complications. But yeah, we really need to think now more in more details in terms of the really model of the Milky Way and orbital motions around the galactic center.
Okay, thank you.
Yeah.
I don't know if there is, I don't see any other hands. So maybe people are waiting for the end, so.
Okay, yeah.
Oh no, actually Vasu is one. Vasu.
Hi. Sorry, this is me. I'm in disguise, but so my question is: you said that you rely on simulations to draw conclusions about the fraction of the cold neutral medium, the warm neutral medium, and the unstable gas in between, right? Do I understand this correctly?
Yes. Yeah, okay. So basically from simulations, we get models and predictions like the right-hand diagram. So basically the simulations are telling us how much of the CNM we should have, how much of the WNM we should have. And then depending on how much turbulence there is in the simulated box, that will change the fraction of the thermally unstable gas. But what we were using simulations for, so this is just basically a pure comparison, but what we were using simulations for is So if you have a simulation which shows you 3D structure like XYZ, and then from there you can make synthetic spectra. And synthetic spectra, I'll show you absorption line features. And for us, we don't know where things are along the line of sight. So all we have is just a spectrum, observational spectrum. So one question we had was, are the spectral lines we are pulling from observations in terms of absorption spectra, do they really correspond to real physical density structures? And that's what we were using simulations for, to essentially quantify how complex is when you are going right through the disk of the Milky Way, where you have so many clouds very close together. What sort of confusion is that going to incorporate or imprint on your absorption line spectra? Because, you know, as you know, like if I have so many clouds along the line of sight, then I do Gaussian line fitting, this is going to cause problems for my temperature calculation. So this is why we were using synthetic data to say, okay, if you're working at the latitudes, observing at latitudes above than 50 degrees, we are doing fine. But if you're, for example, looking right through the disk of the Milky Way, we are really getting confused almost 50%. So basically the temperature measurements there are kind of biased and they're not really correct.
Okay,
yeah.
so my follow-up question then is, what the small fraction of unstable gas that you find in the end, what does it imply about the turbulence in the ISM?
Yeah, so what actually it implies is that, either stellar feedback is not as important as what numerical simulations are telling us, or that as these numerical simulations are saying, that essentially gas, you know, over a very short period of time, gas can reach thermal equilibrium and everything looks okay. Yeah, so I think it's probably telling us something about the time scales on which turbulence operates. And I guess that is really related to the types of turbulent sources. And that's something we really don't know observationally very well. And it's something I'm going to talk about in the last part of my talk. Yes. Or it could be just simply telling us that currently numerical simulations are including way too much turbulence. Something is not right there. Yeah, I can't answer which one of those two.
Thank you.
Okay, so let's talk a little bit about turbulence because that's so important. And so the stellar feedback is through supernovae, through stellar winds, inducing a lot of turbulence into that neutral gas, and that interstellar turbulence affects the structure and kinematics of spectral lines we're observing. So, of course, it will be great if we can constrain different turbulent sources and really figure out observationally which modes they operate, which timescales they operate, on which specific spatial scales are they important, so that maybe we can say, aha, supernovae are really important on large scales versus small scales where something else matters more. So classical way of studying turbulence has been to calculate the spatial power spectrum. And sort of usually we would take observations for a whole galaxy, like the SMC, and run the Fourier transform, calculate the power as a function of spatial scale, and get this one-dimensional power spectrum. And the slope of that power spectrum is telling us something about the mode or sort of a type of turbulence, whether we are dealing with something that comes primarily from shocks and has a very steep power spectrum, or is something mainly driven by large-scale galactic rotation. Similar work was done for the LMC, and for disk galaxies, there is an added complexity where many studies have noticed a break in the power spectrum, which signifies the presence of the disk structure. So essentially, turbulence is changing between being 2D driven within the disk versus 3D driven in the outskirts of the galaxy. So this is all nice, and considering that turbulence is driven by stellar feedback, the logical explanation is to expect a correlation between the slope of the power spectrum and level of star formation in galaxies. So here is an example from a Little Things survey of dwarf galaxies, where it's again the same game. Let's calculate the spatial power spectrum of atomic hydrogen and plot that as a function of star formation rate. And as you can see on the bottom panels, this is essentially all over the place. There is really no obvious correlation. So this was confusing. What's going on here? Is really star formation so important and stellar feedback so important for setting up turbulence? However, there was always a bottom line conclusion that we can't really tell very much because we are dealing with usually hundreds of kiloparsecs resolution for nearby galaxies. But this is changing. With ASCAP, we have beautiful new observations of the small Magellanic cloud, and very soon we will have observations of other nearby galaxies. And what my students have recently done, instead of taking this whole image and boiling all of that down into a single power spectrum, we started taking smaller portions of the image, calculating the power spectrum slope, mapping that, and then keep going spatially to essentially cover the whole image. And so instead of in the past having for a single galaxy just a single power spectrum slope, we end up having an image where each pixel represents the slope of that power spectrum. And the key goal here is to identify local sources of turbulence and therefore constrain directly the influence of stellar feedback locally on the gas and quantify that. Okay, so this is the SMC. The SMC is a very interesting, it's a lower metallicity galaxy, like almost 10 solar. By running some simple simulations, we have convinced ourselves that we don't really see any substantial variations in the power spectrum slope here. So mostly, basically, you see orange and yellow pixels. And yeah, this is interesting. So basically, the conclusion is in the SMC, turbulent properties across whole galaxy are very uniform. Potential reasons for this. One is the metallicity. At low metallicity, molecular clouds tend to be much, much smaller and more compact. So maybe we're still not reaching the scales, small scales on which stellar feedback really operates and prominently shows up. Or the other option is because of the gravitational interactions with the SMC, between SMC elements in the Milky Way, we know that the SMC is stretched along the line of sight. So it could be also that large depth along the line of sight. But yeah, it was definitely an unusual result. So then we turn to the LMC, which we know it's much bigger and also has a much more spatial diversity in terms of star forming regions. And because of the presence of the disk, for the LMC, we now we iteratively have to fit 2 power law slopes for each tiny little kernel across the image. And so what I'm showing here is on the right-hand side, so this is the image of the power spectrum slope predominantly on small scales, scales less than 400 parsecs. And on the left-hand side is a slope on large scales, that N over here. So you can see right away, there is so much more color, there is so much more diversity here. And just to highlight, this was work by 2 undergraduate students in Wisconsin, Sam and Dell. So what we are seeing on small scales is clearly evidence for stellar feedback locally modifying the power spectrum slope. So what's happening is stellar feedback destroys interstellar clouds locally and effectively moves denser medium into something that's more diffuse, effectively shifting the power spectrum and making it more steeper. So this is 30 Dorados, the whopping star forming region in the LMC, where we see that very clearly. So right in the vicinity of 30 Dorados, the power spectrum slope on small scales becomes suddenly much steeper. And numerical simulations have predicted this effect kind of globally in galaxies. So it's a really negative feedback. So stellar winds, supernovae destroy or evaporate clouds, essentially shifting power from small scales into large scales, resulting in the steeper power spectrum. So this is really a nice confirmation of that effect. What's happening on large scales is very interesting and sort of puzzling. So we see in the outskirts of the LMC sudden steepening of the power law, of the power spectrum slope. And on the right-hand side, this is happening exactly at the position where stellar studies have found flaring of the LMC disk. And so our interpretation is that what we're seeing here is also flaring of the hydrogen disk, of the atomic disk, and essentially turbulence going from a 2D motions to 3D motions because of that depth of the gas suddenly becoming much larger. And some simulations for the interactions between the LMC and the Milky Way have suggested that, effectively have predicted that there should be flaring of the H1 disk on both sides. And those sort of elongated orange pieces, which with very steep power spectrum slope, could be really signifying that. The other idea is some ramp pressure as the LMC is moving through the Milky Way halo, but we need to do some more work to distinguish between those two scenarios. And I'm basically at the end of my talk here, conclusions that with deep absorption lines, we can constrain the fractional thermally unstable gas, and we can basically probe and test the predictions for the thermal structure in the Milky Way. And we are already in the process of doing that for the Magellanic clouds and other nearby galaxies. We find that the von neutral medium is hotter than predicted, and that has something to do with the Lyman-Alf flux that is still essentially just being considered as being uniform across the whole Milky Way, which we know can't be true. Yeah, with ALMA-SPONGE, we are trying to use our hydrogen diagnostics to come up with some constraints of what are good physical processes and conditions for the formation of molecules. The power spectrum, the high resolution observations, we can now run the power spectrum analysis and start seeing evidence for stellar feedback locally in galaxies. There are many new radio telescopes happening already, working already or happening in the near future. We'll have ASCAP that's just about to start full-scale observations, NEARCAT, in the future SKA. And in the meantime, a group of us has been using the VLA for this extra large project to do a very detailed high resolution mapping of M31, M33, and 4 galaxies in the local group. And the science questions are really exactly the same and related very much to things I've been talking about today. Constraining cold H1, understanding the role of turbulence, and stellar feedback in galaxies. So I'll stop here and we can continue with some questions. Thank you very much.
Thank you very much, Snezana. It's a very interesting talk. Actually, see, I think Yuga also joined late. We are open for questions. Someone would like to ask something, or?
I would like to ask something. This is Dept
Yes,
here. I just can't find the hand. Hi, Snezana. How are you?
Hi. Hello.
May I go ahead, Vasily?
Yeah, go ahead, Despina.
Yeah, thanks. Snezana was wondering about the SMC results that you described. And actually I was thinking that could the reason be that there's a really global star formation event recently, and that's probably why the turbulence is more or less the same everywhere? Could that be the reason? There's no specific areas where there's very strong star formation, but it's sort of widespread more or less.
Right.
I don't know. I
Yes.
just, yeah.
Yes, that could be, yes. Mm-hmm. There are
Because
lots of possibilities.
yeah, yeah.
Yeah. Another idea is always that because we never really see a break on the large scales, that it's really large scale driven turbulence that's very important, and that could be even coming due to gravitational interactions with the LMC and the Milky Way.
Yeah.
And yes, there are some theoretical studies that suggest that large scale driven turbulence is extremely powerful, and you can even have a lot of small scale drivers, but they can be totally wiped out by the large scale driving. So I guess like unless you have enough or a lot of that small scale driving by stellar feedback, you may not be able to see it. So yes, yeah. So there are several ongoing studies right now. So basically, with a group from Australia, we're trying to calculate the type of turbulent driving that's present in the SMC. So for example, if whether it's shock driven or more large scale gas stirring. And that, once we constrain that may tell us something about the driver. So is it more large scale rotational effects, or is it really more shocks spread out all over the place? So yeah, so that may offer some answers. But yes, we have also done some very simple, just kind of taken some very simple simulations and then say, okay, let's say if I have a box with low turbulence and then a box with high turbulence, which is sort of localized in velocity, and then stack everything along the line of sight to sort of simulate the effect of large line of sight depth. So we notice that even if you have small effects of star formation, if you have a very large line of sight depth, by squishing, integrating everything along the line of sight, you can wash out those small scale star formation effects. So it could be that. It could be also metallicity, because at low metallicity, everything gets down to much smaller scales. So I would expect also stellar feedback to show up on much smaller scales. Maybe maybe we just need to reach to slightly higher angular resolution. But yeah, it's a very interesting question. I mean, I was surprised why it is so uniform.
Thank you, Snezana. Thanks very much.
Thank you. Someone else? Andrea, go ahead.
Yeah, I do have a related question. We do see in the LMC that you find the difference exactly around the areas of the supernova remnants. In the SMC, we don't have such a large population of the supernova remnants. So couldn't this be exactly the reason that the supernova remnants are providing feedback? In the SMC, we don't have that many supernova remnants, so we don't have that much feedback. And the reason is that the star forming activity in the LMC is much, much younger, like it's happening right now, whereas in the SMC, most of it happened several mega years ago. So the question is, if you go in the neighborhood of the known supernova remnants in the SMC, do you see any variation? And if you don't, what does it tell you about the feedback mechanism?
Yeah, that's a great idea, and we are definitely going to look for that. So as I said, this is 10 parsec resolution, and we have already high resolution data. So we can push this down by another factor of 5. And that's definitely going to be helpful. And then we can just look at some specific star forming regions like N66 versus N84 versus the bar region, and see locally whether we can isolate it. Yeah.
Because that might be a way to break the metallicity degeneracy, like the issue of the metallicity, because then you are comparing similar places with similar stellar populations of similar ages. You know the mechanical energy that is entering that area from the supernova remnant population. And then the only factor that is missing is the metallicity.
Right.
That is different, I mean.
Yeah. So there will be more on that, and and also with the other four galaxies from the VLA study. So that's also going to be an interesting example of seeing how important is stellar feedback in supernova in particular. And I'm also aware there was a study by, I think it's a German group, and the first author is Ramachandran, Varsha Ramachandran. So they were studying in the SMC stellar winds. And I think there is a claim that at low metallicity, even stellar winds are less powerful than at higher metallicity. So there's definitely an interesting metallicity effect that could be playing something here. But yes, getting down and comparing really regions of similar age and similar type of activity and looking what that does to the power spectrum would be very, very important. I agree.
Okay, thank you very much.